In the realm of networks, you will find there's all kinds of devices out there. Firewalls, intrusion prevention systems, NAS device. I mean, there's all kinds of stuff that can plug into a network. However, there's two core devices that really make it work. Switches and routers. Both of which Cisco has staked their name on. They will tell you, we make the best switch and router that money can buy. And I will tell you, I absolutely agree. It takes a lot of money and it is the best. So with that being said, switches is where most people get their start into the Cisco world because they take a lot more normal day-to-day stuff, normal day-to-day changes as compared to routers that a lot of times you just set up and forget about unless you are in a very dynamic and expanding organization. So switches are a lot of your day-to-day. So we'll start there here. We'll start there here. Well, did you get that? So we'll look at the different devices, kind of the evolutions that switches have gone through. A big one for your understanding and certification purposes, collision and broadcast domains. And then I want to walk you through an end-to-end scenario, a day in the life of a switch. So the realm is 1980s time frame. Bengals are singing Walk Like an Egyptian. Big hair is the norm. And network hubs are hitting the market. 10 megabits per second speed, screaming this is life-changing events where we now can have computers sharing data without people walking floppy disks back and forth down the aisles. I mean, that's the kind of time frame that we're in. Ethernet is developing the standard of carrier sense, I should say it is developed, carrier sense multiple access collision detection, meaning we have this competition between Token Ring, which is still a valid competition back in the 80s, Token Ring and Ethernet, where Ethernet uses this kind of environment. Multiple people are accessing the network at a time. They're all listening. They're all trying to sense if there's anything being sent on the network. If they don't hear anything, because only, and here's a key point, only one of them can send data or receive data at a time. Only one. And so they're all listening. They're like, okay, is anybody sending any data? No, I don't hear anything, so I will go ahead and send it. And that works most of the time. However, there is a chance that two people are listening at the same time. What if two computers are listening at the same time? They both hear it clear. They both send. That's where we have a collision. And that is collision detection. That's the ability for the devices to be like, oh, we both sent at the same time. Our data is scrambled. My bad. They run a back-off algorithm that they both, back off and then wait a certain amount of time to send again, and then they both send, and they hope that they don't collide a second time because collisions are really taking down their network performance. And that was one of the things with Token Ring. Token Ring said, we're going to send this little ring around the network. I shouldn't say send a ring. Send this token around the network that all the computers are plugged into, and only whoever has the token can send at a time. So this token is going flying at the speed of light around this ring network. The devices are grabbing, adding their data. It never had a collision. That was carrier sense multiple access collision avoidance. Which you might say, well, that's gone, right? Token Ring's gone. Well, yes, Token Ring is gone for the most part. However, collision avoidance has reared its ugly head again. I shouldn't say ugly. It's there in Wi-Fi. Wireless networks don't have the ability to detect collision, so they've gone back to a type of collision avoidance system, but that's a total another topic. So hubs are sitting here in Ethernet, running in such a sense that they have only one person able to send at a time. Now, let me put a definition to that. That is short for one collision domain. Key topic to know. A hub, no matter how many ports it has, it could have, 8 ports like I'm staring at, or 20 or 950,000 ports on a hub that it would not have that, but it would all be one collision domain, which in rough English would just be how many people can send or receive at a time. Now I also want to emphasize the or there. Or receive means you are in a half duplex world. Send or receive. So I'm pretty much saying, well, I can send something or I can receive something. I cannot do both. It's like a walkie-talkie. Now that was the world of the hub. One person sending or receiving at a time. So the larger and larger your network grew, the more and more collisions you would have because there's more of a chance that people are sending and receiving or sending or receiving at the same time. And you're getting collisions. Your network performance is going down. Likewise, you run into challenges with security, meaning a hub, if you bring up the OSI model, got your 7 layers, down here is the physical layer, which is where the hub resides. Physical layer devices have no intelligence at all. They receive electric signals and they send electric signals, and that's exactly what this does. When this guy sends a packet, let's say it's destined for this guy, what the hub does is receive it and say, well, I just got some data. I'm going to send it out all of the network ports. This guy will get it, but so will this guy. So will this guy, and whatever other guys are attached to that network. Now, he's got the sad face because his monitor is not a perfect square, but also because he is a hacker. He is using a program like Wireshark. Used to be called Ethereal, which you can freely download. It's like those programs we just talked about in the console connections. You can just type in Wireshark in Google and download it. And what it will do is capture all of the data that it is receiving on that network port and store it, so you can actually look at it. If you are good at Wireshark, which it takes a little training, but not much. Wait a sec. I've shown you Wireshark. What am I talking about? You know what Wireshark is all about. You can reassemble Excel spreadsheets that are being transferred. You can capture voice conversations that are happening, record phone calls that are being used voice over. I mean, you can see emails that were being sent. I mean, everything is able to be seen because a hub sends everything everywhere. So today, that's enough about hubs because they are network death. You do not or should not use these in production because number one, the collisions alone will slow your network to a crawl. Second off, the security. I mean, it's just, this is yesteryear technology. Also, a hub maxed out at 100 megabits per second. Once it reached that speed, that's where everybody's like, okay, we've gone switching. You won't find a gigabit hub. So we move into the 1990s. The Bengals are now not singing "Walk Like an Egyptian." actually, it's really funny. The Bengals performed at a Cisco Live event. Cisco's big once-a-year conference here in the United States, and they sang "Walk Like an Egyptian," and they forgot the words. They got to like halfway through, and the girl was saying, it's a really fast song. It's hard to keep up with. And she's like, they forgot the words to their own song, and they made a joke about it. It was funny. Nonetheless, the Bengals are forgetting their own lyrics. We're coming out with network bridges in 1990s. The network bridges was this transitionary device between the hubs and switches, which broke the network into multiple collision domains. Now, looking at it, I couldn't find a picture of a network bridge. Looking at it, you can't really tell much of a difference other than bridges had limited ports. You wouldn't find a 32 or 48 or 64 port bridge that you would plug your devices into. These were really expensive devices that you would have your hubs, with all your devices attached. And as it started maxing out, like you're getting a lot of collision, you would introduce a bridge. Which would have maybe 2, maybe 3, 4 different ports on it. And that bridge would separate the multiple hub-based domains. Remember, over here, only one person can send it at a time. So a bridge would, number one, introduce more than one collision domains. Every port on a bridge is a collision domain. So over here, we can have one person sending or receiving. Over here, we could have one person sending or receiving. So now we can have multiple people sending or receiving at a time on the network, and the bridge is now introducing intelligence. OSI model, we're now moving up to layer 2. We're at the data link layer, which is where this device resides, and it learns the MAC addresses. So the hub, we've got, we'll say 10 computers over here and 10 computers over here. This bridge, as the computer are sending and receiving, it's learning which MAC addresses or which data link layer addresses are on each side of the network. So now you get some limited filtering. When somebody sends something that belongs on, let's say, this side of the network, let's say this guy sends, it hits the hub sends it everywhere. Including the bridge, and the bridge goes, oh, well, it looks like that was sent to this MAC address. We'll call him MAC1. That was sent to this MAC address over here, so I'm not going to forward that on to this side of the network. They don't need it. So that's where our filtering came into place. Now, if you sent to the other side of the network, let's say we sent from the left side of the network here over to the right, as soon as it hits this hub, it explodes and goes everywhere. So you're not really getting much filtering since we still have these layer 1 devices, but it was good. I mean, this was a good step. Now, here is the big Achilles heel of the bridges. They were software based. So these guys would slow down your network. I mean, when I first started teaching, I actually started with Novell and then moved into Microsoft technology, talking about like Windows Server MCSE certification back then. And one of the things, I still remember this for some reason, I was talking about how Windows 2000, I think it was, could do RAID. Meaning it could do RAID level 1 or RAID level 5, which is mirroring two hard drives together. And I had a guy in class go, yeah, like I would, he's kind of like, I would do that with Windows. And back then I didn't know better. I was like, well, why wouldn't you do it with Windows? He goes, no. We buy separate hardware to do that. We buy RAID controller cards, which are now common everywhere. RAID controller cards that offload that, so Windows doesn't have to worry about mirroring those. Well, in the same sense, Windows would slow down a lot if you actually tried to do RAID with it because it's having to keep up with hard drive functions. Same thing here. The bridge is learning all these MAC addresses in the software. It's processing them in the software. So as stuff goes from one side of the network to the other, it slows down because of the processing that's taking place on that device. And now we make the turn into the new millennium. Around year 2000, you start seeing network switches becoming a commonplace thing. I'm thinking, okay, we had the 80s, there's the bagels. What do you say happened? What happened around the turn of the generation? I mean, it's like the Y2K scare. Well, that's an event. There's nothing that really characterizes things that have happened. Maybe the dissolution of normal relationships to where now everybody communicates via texting and Facebook and no longer face to face, because that's weird to actually see somebody and talk to them. I'm saying that's weird to have natural relations. Here I am talking to myself, staring at a screen. Yeah, I'm a lot better, right? So anyway, here we are in this switching world. Every port now has its own collision. And you know what? Let me actually move this to the top, because everything that I said about bridges is the same when it comes to switches. However, we now have a very high port density. Like a lot of devices can plug into these. We're no longer limited to 2 or 3 or 4 ports. But the biggest thing that changed was the creation of ASICs. What are those? Application-specific integrated circuitry. Such a huge concept for our network devices, because this moved that software-based processing of the bridge into the hardware. And you're going to see this topic come up again and again and again and again. All ASICs are is somebody engineered a chip. Here's my little chip, a little chip with wires and connections and all that kind of stuff, to where in the hardware, the intelligence of the device, it's able to handle it without relying on any kind of software. And anytime you introduce ASICs into the picture, you introduce a lot of speed because you have it all being processed in hardware. No longer does the software have to get involved. ASICs has changed the world of switching, or bridging, I should say, to where now switching is commonplace. ASICs changed the world of VPNs. We would no longer be able to scale virtual private networks, which is encrypted tunnels running across the internet, if we didn't have these ASICs, these chips that handle a lot of the encryption, because the encryption alone would bury the software of the device. So ASICs are a world-changing event that they caused a lot of these devices to just move a lot faster. Now we have switches where it's able to move as fast as the hubs were, which is wire speed. As electric signals are coming in, it's processing and sending them out. Every port on a switch is its own collision domain. So when you come to a switch, you look at how many ports there are. Let's say it's a 24 port switch, or this one looks like a 20. They got these 2 weird ports, so maybe a 26 port switch. So you've got 26 collision domains. And again, going back to our simple definition, 26 people, 26 devices plugged in there can send and, there's a big change, and receive at the same time. We've gone full duplex to where now instead of a walkie-talkie, you're like a telephone, to where both people can talk on top of each other and still understand, at least in the computer world, still understand each other. So when you say this is a 100 megabit per second switch, or 100 megabit per second port, really you're getting 200 megabits per second if you're running it at full duplex, because you get 100 send and 100 receive that you can do at the same time. Now, all network speeds are rated at half duplex. So when you see a gigabit or 100 megabit per second port, it's being rated at half duplex. So you truly can never go above that speed. It's just now you can do send and receive at the same time. It's totally kind of life-changing event there. You also support varying port speeds. A hub had to have all the same speed. If it was a 10 megabit per second port, every port on that hub, a 10 megabit per second hub, every port on the hub would be 10 megabits per second. But with switches, you could have, for instance, these guys, and this is common, over on the left being 100 megabit per second connection, and these two guys over on the right might be 1,000 megabits per second or a gigabit. Or as technology continues to evolve, we're going to see these being common. 1,000 megabit per second ports is normal customer plugins and in normal use, and then maybe these uplinks are 10,000 megabits per second or 10 gig or now 40,000 megabits per second or 40 gigabits per second uplinks that you can have. So that way you can have switches that are daisy chained together, to where you've got all these guys that are all 100 and this is 1,000, so that way this doesn't become a bottleneck, and all these guys are 100 and this is 1,000. So that way you can link these together without bottlenecking them on these speeds. These switches are managed and intelligent, to where, and I'll flip that term, they're intelligent in the sense that they have the same capabilities of the bridge to learn MAC addresses. So as these switches power on, they will learn all the different devices that are on there. So now when this guy sends a packet into the switch, it will be able to send it out to just that guy because he knows where the MAC address is at. He's located all of it. He will even learn, for instance, if you start daisy chaining them like this, you've got 20 MAC addresses down here, we'll say that it's learned. This switch will learn that all 20 of those MAC addresses are accessible on this one port. So it's not uncommon to see one port with 20 MAC addresses, which tells you, okay, that port must be daisy chained to another device that has all kinds of devices plugged into it. So that's the intelligent side. The managed side is going to be what we get into with the Cisco IOS. We can do things with our switches. We can change things. We can modify settings. We can add features. Now, one of the nice things about Cisco switches, out of the box, they work. Yeah, that's great. You plug them in, you plug in your computers, and it's working like a switch, but you're only getting, a limited feature set by doing that. You're just getting the base functionality. You might as well go buy, some other brand, or what you'll hear is an unmanaged switch, which doesn't really have the iOS. It doesn't have features. You just plug it in and plug stuff together, and it just kind of works. It learns MAC addresses and does its thing. Cisco adds features that you can configure. That's going to be what we talk about in the switching world. Now I know you're looking at, I was just thinking of what else about these things. They smell good and they're smooth to, now I'm only half joking. When you open, if you have the privilege of opening a Cisco switch, it has that new cellophane smell. It only lasts for about 10 seconds after you pull it out of the box. It's so good. After you've opened a number of these devices, initially you're like, oh, that's repulsive. But after a little while, you're like, man, I love that. It's like the Pavlov's dogs, kind of jingle the bell. Like when I smell that cell phone, I'm like, ooh, new Cisco device. Where is it? It's so it smells good and it is smooth to touch. It is. You install these into racks. I'm kind of tongue in cheek on saying that, but this is the core of what our networks use to connect devices. One more piece that I want to add on here, because it was on the title side, I didn't add it in my bullets, is the concept of a broadcast domain. A broadcast domain essentially means how far will a broadcast message go before it's stopped. Okay? So a broadcasts just happen in the network world. They're partially how computers work. Like when this computer boots up, if it's using DHCP, it doesn't have an IP address. So it will send a broadcast message saying, hello, anybody out there? I don't have an address, an IP address, I should say, but if somebody could give me one, that would be great. It's looking for a DHCP server. Now, on a switch, just like a hub, broadcast will go to all ports. That's one of our scalability concerns. A hub, you can only scale to a few devices. I mean, 30, 40 devices, you're starting to really hit the max. Switches, you can get into the hundreds of devices, 200, 300, 400 devices, but eventually you're going to reach a point where you get so many broadcasts because everybody's kind of chitter-chattering around that you're impacting your computer and network performance. So you start dividing it up into more broadcast domain. We'll talk about how that's possible, but I just wanted to throw that term out there so it starts sticking in your mind. All right, the last thing I want to do is give you a day in the life of a switch. Like if you want to see a switch's job day in, day out, like time to make the donuts kind of job, this is what it looks like. We've got our network devices, in this case 5 computers, that are plugged into 2 different switches. Now, the first thing I wanted to do, I threw 2 switches up here because I wanted to show you this cross connect. Now you can connect switches together on the Ethernet ports, no problem at all, using just a normal crossover cable. Or nowadays, they have the auto sensing ports that allow it to detect a crossover straight through and make the adjustments accordingly. But that's one way to bridge them. The challenge with Ethernet is that you have a 100-meter limitation. So once you exceed that, now you're kind of stuck. So a lot of people will start going with things like fiber. A lot of times there will be buildings across the street from each other. They need to run cables that's longer than 100 meters or just a really big building. So they'll start putting fiber in here. This is actually known as an SFP module. It's a fiber optic module that you can slide in there. You buy them separately. I think SFP stands for Small Form Factor pluggable. I had to pause and look it up. Everybody just says SFP. For some reason, the acronym isn't used very often. But this has a fiber optic connection. Now, on fiber, you always have 2, I guess you could call them wires. They're not really wires. They're glass or plastic that are in there. One is going to be a send, and one is going to be a receive. So you kind of go click, click, and plug it into that. And then that fiber, depending on the kind of fiber it is, you could go 500 meters away. You could go to, miles, or depending on where you are in the world, kilometers, depending on what currency you use for distance. So you can span these things way apart and connect them just the same. So a lot of times on the switches, you will see these ports that are kind of dual purpose ports, to where you can either, this is like a Cat5 connection or Cat6 copper connection. And then below it will be an SFP where you can plug in one of these fiber optic modules. Or you might see one, I think this is one of them. I don't think these are dual purpose, where you have 4 slots where you can plug in SFPs. Now you might say, why do you have them changeable? Well, there's different kinds of fiber that you can get. There's multi-mode fiber, which is really easy to work with and a lot cheaper to make because it's plastic. And so multi-mode fiber has the ability of being really easy to work with and really cheap, but it doesn't go as far as single-mode fiber. And single-mode fiber is always glass. If you were to open this up with a little razor, and you would see that really, really thin glass that it's using, and a lot more difficult to work with and a lot more expensive. So based on what your needs are, you can buy single mode or multi-mode fiber interfaces, and then you just have to, you just got to make sure they're compatible. Make sure, essentially the cable type and the connector type. There's different kinds of connectors for fibers. This is an SFP style connector, but they have, big connectors, small. You just got to buy the right cable for the job. So that's how you connect them together. Now, a little fiber optic lesson aside, let's talk about the communication. And clear off all my gibberish. When you first boot up these switches, they have something known as a CAM table. And the CAM table is essentially empty. CAM stands for Content Accessible Memory. It's a place in memory where it stores stuff, and in this case, the CAM table is going to include our MAC addresses that it's going to learn from our different devices on the network. So when we first boot the switch, it's completely empty. So let's say, now we've seen our MAC addresses. MAC addresses are 12 characters, so let's just say this happy computer right here is 11:11:11:11:11:11:11. You'll see them written this way. That's a common way to write a MAC address. You'll also see them written this way. This is a lot of times what you'll see in the Cisco world, 2222, 2222. Or Microsoft, a lot of times, like if you do open a command prompt and do an ipconfig, Microsoft likes using dashes. So for instance, it'll show you MAC addresses like this. So I'll make this guy, let's just use all three styles here on the screen. 33, 33, 33, 33. So really the style doesn't matter so much as that there's 12 characters inside of it. So every MAC address is 12 characters long. So this guy, let's say the guy on the left, the happy computer, is talking to kind of the straight face computer in the middle. So he's going to send a frame. Let's just say I ping. Let's see what. I'm trying to think how far back I'll go here. Okay, so let's just say IP address wise, this guy is 10.1.1.1. This guy is 10.1.1.2 on an IP address. So on this computer, I type in ping 10.1.1.2. Right? What's the first message that's going to be sent? An ARP. Address Resolution Protocol, saying, okay, great, I see that you're pinging 10.1.1.2, but I got to create a frame. I got to have source and destination IP addresses, source and destination MAC address. I don't have the MAC address for 10.1.1.2, so ARP is a broadcast message. So it's going to say, hello, network. Who is 10.1.1.2? So that hits the switch. Now both of these switches are now considered one broadcast domain. So it's going to receive that broadcast and send it out all ports that are active. I mean, there's nothing plugged in. So this guy gets the broadcast. This guy shoots across the fiber. These two get the broadcast saying, who is 10.1.1.2? Now, this is the only one that will respond to that one. So the straight face computer comes back and says, oh, that's me. So I am, and I jumped a little ahead. He goes, oh, that's me. I am 2222. This is my MAC address. But let me take a step back. As soon as this broadcast came into the switch, I mean, if we were to grab that and use Wireshark and look at it, we would say, okay, it's an ARP message. It's trying to find a MAC address. It's coming from the source IP address of 10.1.1.1. It's looking for the destination IP address of 10.1.1.2. It's coming from the source MAC address of 111, this guy right here. And it's going to the destination MAC address of, I don't know. Now you might say, well, wait a second. It doesn't know this MAC address. It has to have something in there. Well, it absolutely does. Its destination MAC address is FFFFF. Remember, MAC addresses are hexadecimal, so A through F are valid characters, and the very, very last possible MAC address in all the scheme, FFFFF, means a broadcast. That's what that means. So the switch receives it destined to this MAC address that it will never learn on any individual port. And it says, okay, well, that MAC address says go everywhere, but I just learned something. By seeing this broadcast message come into the switch, it goes, oh, whoa, wait a sec. On port, let's just say this is port 0/2. This one up here was 0/1. So it says, okay, 0/2 is really 1111, 1111, 1111. So now the switch has become one MAC address smarter. Now this guy comes back and says, oh, that's me. Let me send my ARP reply. Here's his ARP message. I'm coming from this source IP address, going to this destination, coming from this source MAC address, going to this destination. Let me just zoom in on that. If I were to break that packet down, it would say the destination MAC address is the ones, the source MAC address is the twos, and it will come into the switch. Now two things happen here. One is, let's say the switch is looking at, let's just say that is port 0/12, or let's say 0/11. Well, no, it's probably, I'm trying to be accurate looking at the switch. Let's say 0/15. So it's going to say, okay, I just learned another MAC address because I just saw a frame come in there. It is 2222. So I now know that computer is available on port 0/15. Now this is all in the CAM, all in the memory of the switch. So if I pull the plug on this switch, at any time, all of this goes away and it has to relearn all of these MAC addresses. But so that's the first thing it does, is it learns that MAC address is on that port, but now it's become smarter. It goes, oh, it looks like you're trying to go to the destination of all the ones. I know where that guy is. He's on port 0/2. So now, instead of sending the reply to all ports, the switch is just going to say, okay, let me switch you right over here down to this device, and only those two get it. And now point-to-point communication can happen between those guys without disturbing anybody else because the switch has learned their MAC address. Now let's talk of real world. Okay, a switch powers on. How long is it going to take before it learns all of the MAC addresses on the network, or the ones that it needs? I would say 5 to 10 seconds. I know. Like, really that fast? Yeah. I mean, hundreds of devices it can learn in 5 to 10 seconds because all of these guys are talking. And if you're talking about powering on a switch, well, as that switch is powering on, the devices are chatting. They need IP addresses. They want to communicate. So the switch is gaining knowledge essentially right after it boots and is ready to do that. It's ready to go. So it does not take long for these guys to learn at all. Also, keep in mind, these entries have a lifespan of 5 minutes. Meaning if the device goes quiet for 5 minutes, and this is by default, you can change it, the switch will forget where that MAC address is. So this guy goes quiet, he disappears from the table. Now, no big deal. That just means the next time somebody has to communicate with him, the switch will treat it like a broadcast because it's going to say, oh, I don't know where 11111 is. So it will send it everywhere and then relearn that. The reason it does that is because MAC addresses can change. Now, it's rare, really rare for a MAC address to change, but somebody could replace a network card. You could be, doing strange things with virtualization. We'll talk about that later on. But, there's times where the MAC address can change. So this guarantees you that device within 5 minutes will be able to communicate or be learned or that MAC address will be replaced on the switch if it stops talking. Welcome to the world of switching indeed. That is how a switch functions. That is its goal, is to bring together all the devices into a local area network and allow them to communicate. So what did we see and what do I want you to do with it? Well, you see the bullets on the screen. Those are the major points that we hit. First thing I would like you to do is grab a piece of paper and in your own words write down a hub is this. Or if maybe you're not a writer, go to a friend, go to a spouse and explain to them a hub is this. This is the difference between a hub and a switch. Or I do this sometimes. I'll be in Best Buy or one of the the places where you just go and waste money on nonsense. But you'll be in Best Buy and talk to one of the employees and see their perspective on it. I've got some very interesting results from my surveys where you just go in and say, hey, I'm looking for a switch, just a small one. Where are those at? Oh, they're over here. Here's the box. And then throw this kind of question out there. Just say, actually, somebody told me to get a hub, and someone told me to get a switch, and then someone else said they're the same thing. What do you say? What's best? And see what they say. That is one of the most fun. Now, don't throw them under the bus. Don't be like, okay, no, this is really how it works. But sometimes you will get people that are like ninjas, that are like, they know exactly what. Other people will just say, I don't know. Other people will just make up the most creative and unique answers that you've ever seen. Sometimes they'll look at the box and see if it says something, but it's fun. It's a fun survey to take. Second thing I want you to do is look at some devices and identify how many collision domains, how many broadcast domains exist on each one of those. Now, if these are all daisy chained together, if I take some cables and go clink clink and link all these together, how many broadcast domains? One. A broadcast will go everywhere on those switches. How many collision domains? Well, start counting. 1, 2. That's the console port, so don't count that one. Start counting those up. So if you're preparing for certification, be ready to answer those kind of questions. Like just based on these devices and how they're connected. How many? You'll see some hubs mixed in with switches. How many collision domains exist and all that. Now, there's a question. What if I take a hub and plug it into that switch port? Okay, now how many collision domains do I have? If I'm just talking about that realm of it right now, one. It's just one, because it doesn't matter how even though I'm plugging into a switch, still only one device on that port is able to send or receive. We've gone back down to half duplex because we're in a hub at a time. So again, drill yourself, go through systems like that, and then finally, now just understand how the switch is doing what it does. Look at that day in the life of a switch. See how it learns the MAC addresses and becomes just more efficient as it runs. I hope this has been informative for you, and I'd like to thank you for viewing.